in case you're interested in this sort of thing, what I've talked about up here in words is that when we look with the camera, we are viewing in spherical coordinates. And then we can transform from spherical to Cartesian coordinates, and that's how we get the third dimension out of it. This is the mathematics involved with that. For the left and right on the TV camera, the equation is this. That's what we see, and it contains both those components. Here's the up and down, same type of thing. I don't know if we really need to go into what these equations mean, but this shows you how you can transfer and get all three. Notice there's x, vx, vy, and vz. So if you can solve these equations, you get all three velocity components, and so that's how it works.
And ultimately that tells you a three-dimensional movement of an object rather
That's
than
right.
a two-dimensional.
You're not constrained to a flat TV screen anymore. You know exactly where it's going in space.
Okay.
And that's really what finalizes what I've been able to do.
Okay.
Well, let me show you a couple graphs that I have made once I got this data from the people that were taking a frame-by-frame position of the main object. I graphed the left and right position of the main object as a function of time, and this is what I've got. Now this is a broad scale graph of that, and I'll show you a close-up in just a little bit, but there are several features we want to notice here, and we'll come in closer and look at this in just a second. But see this little tiny tail here? Doesn't look like much until you come in close, and then you can see it. It's pronounced enough so that it's significant, but the fact that that goes down and to the right means that the main object on the TV screen is moving to your left, as you saw in the video. And the fact that this goes up and to the right means that it has reversed and is going back and to your right on the TV screen. And if we want to believe that this thing is an ice particle, if we look at this graph, we see a tremendous problem right here. What the object does along this line, that line is neither going up nor down. And what that means is it has stopped dead in its tracks, and it stops for a full half second. And so the question might be, well, where did the flash occur? Sometime in here, of course. And so if the scenario is flash and then exhaust comes up and then ice particle moves, you've got to have a 1, 2, 3 sequence. The flash has to come first, and then there has to be a time lapse, and then the object has to either stop or accelerate back in the other direction. It can't stop before the flash or
Right.
at the flash.
You mean dead in the air?
It stops absolutely dead in the air for a full half second.
And there's no way physically possible within our physical understandings that any object could do that?
Well, if it's a spacecraft, you can put on the brakes,
Yeah.
of course. But if it's an ice particle, that's a real problem. Let's look at this a little bit more closely. I have marked here where the flash occurs. And there's also a pre-flash that's tough to see on the original film as you watch it, but it was pulled out by the people in Milwaukee that did this for me. There was a tiny pre-flash and then the regular flash, and those are of different durations. Here is just the rough data, not smoothed at all. There is the stopping right there. The pre-flash actually occurs as the object is moving to the left. So you think, I want to save this ice particle theory. How about this? What if the pre-flash stopped it? And so it sits there, and that was a rocket flashing and then stopping it. And then you have the main flash, which is then going to push it. Well, number one, it would be an extraordinary coincidence if the pre-flash pushed it just enough to stop it. It should maybe slow it down or push it in the other direction, but it would be an extraordinary coincidence if that were to happen. But also, using the analysis that I explained on the board and pulling out all three velocity components, I've been able to tell what direction the object actually was moving in before the flash. And let's switch to the shuttle model here, and I'll explain that. Here's our shuttle. Now, you tell me how this could work. If it's an ice particle, it's somewhere up about here. And I can prove, using what the methods that I just pointed out, that before the flash, before the pre-flash, it's moving like this, in this direction. And the reason it stops then has to be that something is pushing back in this direction. Obviously, that can't be the shuttle. So the pre-flash explanation doesn't work. The reason that object, whatever it is, stops is not one of the attitude adjuster rockets. So we have a tremendous problem because it stops right at or just before the main flash. And it simply can't do that if it's an ice particle, and that's proof number one, that it can't be an ice particle. So if we ignore that and go on, I guess, you can't really do that, but you can ignore that and go on, then we can analyze the second object, and I think I'll skip that graph and maybe just go back to the original picture, and I'll show you proof number two that it can't be an ice particle. The second proof is probably best illustrated by an analogy. Imagine for a minute that there was a dandelion seed floating out here, and I were to blow on it. If I were to blow on it, it would move directly away from my mouth. And so if I wanted to find where my mouth was by studying the trajectory of that seed, I would draw a line straight back through where it was and how it had been going, and somewhere along that line would be my mouth. Now consider if we had two dandelion seeds and they're floating out there like this, and I blow both of them, then they both go away from my mouth. And then if I want to find my mouth, I really can do it, because I just have to trace both of those back along the straight lines that they're moving in, and wherever those two lines meet is the location of my mouth. And so I could find out where my mouth would be. And it would be the same with the attitude adjuster rocket. As it fires, then, if those things really are ice particles sitting out there, the main object and the second object below that, then they will move away from that attitude adjuster rocket. And so if we draw a line along their trajectories back, that line should meet, and it actually should meet where the attitude adjuster rocket is. Now, we have to make a little bit of an adjustment for the second object, because it's not completely at rest. It's drifting up just a little bit. So we can account for that by taking the slope of the line afterwards and comparing it with the slope before. It's not that complicated, but it's difficult to explain in words. And we can compensate and take out that extra motion and then draw a line straight back. And that should be the extra added velocity from the attitude adjuster rockets. So if we draw those lines straight back, they should meet at a point, and that point should be the location of the single attitude adjuster rocket that could be doing all the funny business. Here is a diagram of what I've just been saying with words with our dandelion seeds. Here's the main object coming over here, back up like this. We draw a line back along that trajectory, and that somewhere along that line should be the location of the attitude adjuster rocket. And this is the second object here. This triangle, along with the calculations that I've made, enable us to take out the velocity that it had before, which is this little amount here, and then to find out where we should draw our line, which starts along this here. And so if we draw a line from here back in this direction, that's the added velocity that has been given to the second object, and so this should help us track and find where the attitude adjuster rocket is. And I think it's rather obvious that these two lines will never meet. They actually diverge substantially, and they have to meet if they're being pushed by an attitude adjuster rocket. So that's the second proof. Those lines must meet, and they obviously do not. Another thing that I touched on a little bit earlier, but I should be a little more specific about, is that the vernier rockets in the shuttle fire in 80 millisecond pulses. They can fire continuously, but they have to fire for at least a full second, up to 125 seconds, if they're going to fire continuously. So pulses or flashes from vernier rockets have to be 80 milliseconds long. This is a light curve that's been calculated and graphed by Jeff Sanio, the MUFON photoanalyst. You can see that this pulse rises and then just gently trails off like this. Jeff has corrected this curve for persistence, that is, the fact that some light may bleed over and stay in the next frame. He's taken that out, so this should be fairly close to the actual light curve. As you can see, you'd have to calculate this, but from this end to this end is 400 milliseconds. If we extend this one more, maybe trail it out one more, that pulse would be an entire 400 milliseconds long, not 80 milliseconds, and that's really not what the shuttle does. The pulses on the vernier are 80 milliseconds long. 80 milliseconds is roughly, about this, something like this. So the peak should come up and go down in about that period of time. And obviously it does not. I don't know if I want to elevate that to the level of a full proof. I mentioned earlier that I have 4 proofs. I probably should say I have 5. It becomes kind of arbitrary what you would call a proof, and this almost might be a proof in itself. That this pulse is too long by a factor of about 5. The shuttle does not fire in 400 millisecond pulses. The pre-flash is also about 150 milliseconds long, which is almost twice as long as it should be, and that's another problem with this. So that part does not fit either. Now let's go to the third proof, assuming again that the object is an ice particle. This comes from a comparison with its actual speed as calculated from the film in feet per second, and the theoretical speed that it really should have if it's being pulled along by the exhaust from the attitude adjuster rocket. That involves what we call a drag force, and it works something like this. If you have an object sitting out here, and then the exhaust is coming, let's assume that the object is very big and not even going to react. Then the exhaust comes and it just kind of blows right by it, and the object doesn't move at all. And the time that the object feels the exhaust is the time it takes for the exhaust to pass by. But if the object is a little bit smaller and the exhaust is a little bit stronger, then when it reaches the object, it's going to start pulling the object along with it. And so it'll be a little bit longer before the exhaust gets by, and then this just continues on with a constant speed. So it will be pulled along and sped up by the exhaust as the exhaust passes. Now you can calculate theoretically and make a ratio of the amount of time that the object is in the exhaust and compare that time with the length it would take for the exhaust to pass by an object that doesn't move. Take that ratio, and using that ratio you can figure out how fast the object has to be going compared to the exhaust when the exhaust finally gets by. And when you put the numbers in, the object in the film was accelerating for 1.7 seconds. The length of the exhaust was about 0.4 seconds, or 4 milliseconds. Put that all in the equation, and it turns out that the object would have to be going at about 98% of the exhaust velocity of the vernier rocket. I think I mentioned earlier that it's about 8,000 feet per second. The actual velocity of the vernier at that angle would probably be between 84 and 8,500 feet per second, which would put the velocity of the object, the ice particle, at about 8,300 feet per second because it accelerates for that long. So we can figure that out from the numbers that we have on the tape. The ice particle should be going at about 8,300 feet per second. Now, let's take a look at how we'll figure out the actual velocity of the ice particle. We have the velocity, the 3 components, as we mentioned, but the velocity is in just pixels or little bits on the screen per second, not in feet per second. So here's how we locate where the object is. Here's the camera, pointing up about like this. The object is about over here. So let's say there's a line between the camera and the object, and we don't know where the object is. It can be anywhere from the camera out to the horizon. So it's somewhere along that line, somewhere. Now, to locate where it has to be if it's an ice particle, we take the direction of the velocity that we've found, and we point up from the attitude adjuster rocket, because if it's the rocket pushing, then it has to push it in the direction that the object goes. So there's a second line. There's one line there. There's one line there. Where those lines cross, or almost cross, is where the object is. And that's how I've found out where it has to be if it's an ice particle, and it's about right out here somewhere. Mm-hmm. And so there's where it is. Once you've got it out there, you can then translate your pixels per second to feet per second and really find out how fast it's going. Now, there are 2 ways to calculate what the actual exhaust velocity of the rocket would be. Number 1, we know that the object starts being pushed or accelerating at a certain time. We know when the flash occurs. That's a time interval. We now know how far it is from the rocket out to the point, so that's a distance. And how do you figure out a velocity? Well, you divide a distance by time. You travel 100 miles an hour for 2 hours. What's your average velocity? It's 100 divided by 2, or 50 miles an hour. So divide that distance by the time it takes for the object to start, and you've got your calculated exhaust velocity from the rocket. And so knowing where those lines cross then, we can put in the numbers, and when I've done that, I've found that the actual speed of the object, if it's an ice particle, as calculated from the data on the film, would have to be between 5 and 6 feet per second. And we just saw that it really has to be about 8,300 feet per second, and those are so far apart that you just can't even compare them. 5 to 6 compared to 8,300. So that's, I think, a very strong proof that the object in question, the main object, could not have been an ice particle. It's just simply by orders of magnitude not going nearly fast enough. And that's our third proof. So we'll go to the fourth proof, which is a little bit simpler and goes a little bit faster. It comes from a calculation of distance traveled by the exhaust and time it takes for the ice particle to react. This is something you can almost do in your head. For example, if you go 100 miles an hour and it takes you 2 hours, then your average velocity is 50 miles an hour, 100 divided by 2. We have the same thing here. We have the object out here someplace. We have the vernier rocket firing, and we know that it takes about half a second before the object starts to accelerate. If we assume that the flash is a vernier rocket firing, then at the beginning of the flash, the exhaust starts coming out. The object, again, waits for a full half a second before it starts to accelerate. That means that it took half a second for the exhaust to get out there. And since we know the distance that it takes to get out there, the distance is about 65 feet. I think I said earlier it's 95. Actually, it's closer to 65 feet. We have that 65 feet divided by the 1/2 second. It's like 100 miles divided by 2 hours. 65 feet divided by 1/2 second, that gives you a speed of about 130 feet per second for the exhaust. Now that's wrong for the exhaust, but if we assume that that's what happened, that's what was on the film, then the object has to be going at 98% of that speed. Let's just call it 130 feet per second. That is obviously not the 5.5 feet per second that we actually measured. So that's a fourth, simpler proof that the object was not an ice particle. Why don't we sum up the third and fourth proofs? I have another little thing to look at here that puts it all together for us. The speed of the ice particle, since it accelerates for 1.7 seconds, since it accelerates that long, it's got to be going at about 98% of the exhaust velocity. Therefore, it has to be going at about 8,300 feet per second. It must be doing that. If you take proof 4 and take the distance divided by the time, it's going 130 feet per second. That obviously is far off from the 8,300 feet per second. If you take the actual data and the location from the direction of the velocity afterwards and also that line out to the horizon, it's going between 5 and 6 feet per second. All three of these numbers should be the same number. And since they're not, I guess you might make 3 proofs out of it. I'll be satisfied with saying there are 2 proofs here. And all three, again, should be the same, and they're not. And so that's not consistent with an ice particle theory. And that summarizes proof 3 and 4. We can go on to proof 5 now, and I guess we can call this proof 5. I mentioned earlier that we had 4 proofs. It sometimes becomes kind of arbitrary what you want to call a proof, but we can probably make this a separate proof by itself. What if we say then, all right, the 5.5 feet per second just doesn't work. Why don't we take the distance out to where it would have to be in order to have this 8,300 feet per second, and see where the ice particle would have to be to do that. And that's a rather simple calculation. And I've done that, and let's go to the blackboard and I'll draw a diagram for you and you can see how that works. This will be the ice particle. And probably stretching our credibility a little bit here, so we'll put quotation marks around it. This will be, that would be where the shuttle would be. And this is by no means a scale diagram. The shuttle would be an incomprehensibly tiny dot on this scale. We're looking down from the top in case you couldn't notice from that. Anyway, it turns out that if we make the ice particle out where it has to be to have a velocity of 8,300 feet per second, this would be a little bit over 22 miles. We'll round it off, 22.2 miles. And what's even worse about that, now it's kind of hard to imagine how you would see an ice particle out that far, much less how it got out there in the first place from the shuttle. Anyway, that's where it'd have to be to have the correct velocity to make that work. What's worse about this is, remember, we know the direction that the object goes after the flash. And the direction is up something like this. And so, if you trace that back, then that's where the attitude adjuster rocket would have to be, which is just under 15 miles, about 14.8 miles from the shuttle. So the attitude adjuster rocket would have to be clear down here to push it in the correct direction if it's out where it has to be to have the correct velocity. So this is a fifth proof that I would consider, and again, nothing fits. In fact, maybe what we should do is summarize all the evidence now and see how this all works together. So let's run through our 5 proofs and see how this all works together. I made out a sheet for summary of arguments for the ice particle theory, but there wasn't anything I could put on them. There really wasn't anything in my analysis that supports the ice particle theory. You might say that, oh, it's going in the right direction if I put it out at 65 feet or so, but that's only because I assumed that in trying to make it fit. And so there is really virtually no evidence that supports the ice particle theory when you do a quantitative analysis from the frame-by-frame data that we have here. What do we have that indicates it's not an ice particle? Well, proof 1, the main object stops at the beginning of the flash and waits for half a second before it accelerates. And the force that stops the main object is directed toward the shuttle from outer space. None of that fits. It can't stop and just sit there. Moreover, the reason it stops is because there was something directed from it from outer space toward the shuttle. I can't imagine how a vernier rocket could behave in that fashion. Secondly, our dandelion seed analysis, those 2 lines, remember, they should have come together at a point, and they obviously diverged. And even when we adjusted for slight motion for the second object, there was no way that those 2 lines would come together. And they must come together if there is a single rocket that's doing that. They did not. The third, the number of the actual number of the ice particles, well, should be about 8,400 feet per second or so. The actual exhaust velocity is about 8,400 feet per second. And when we calculated, this is actually the 4th proof, we got a 130 feet per second. And then we also calculated that from the film, the velocity was about 5.5 feet per second instead of what it should have been, about 8,300 feet per second. And then finally, the proof that we just looked at on the blackboard, if we stick the object out where it has to be to have the proper velocity, it's 22 miles from the shuttle, and it's pushed by a rocket that has to be about 15 miles down from the shuttle. And so when you put it all together, there just is no evidence from at least the film that I've analyzed. There's nothing that I can find in here that even remotely supports an ice particle explanation for this. And so we have to look at other possibilities, and the other possibilities are not very abundant. You can try to make them into tiny particles close to the shuttle. We've already talked about that. The shuttle was focused at infinity, so any little tiny particles by close, of course, I mean right by the camera, not dozens of feet away. And so that won't work because it was focused at infinity. And then we can rule out more mundane things out in space, like comets and space junk and satellites. They just simply don't change direction like that. And that really leaves only one other possibility once you get beyond the ice particle theory, and that's that these objects were spacecraft. And then you start asking yourselves questions about what were they? Were they extraterrestrial or terrestrial in origin? They're one or the other. And what were those streaks that went through there, and so on, that whole business. Aside from those 5 proofs, there are some other things that possibly I wouldn't elevate to the level of proof, but might be. First of all, I mentioned that the pre-flash lasts for about 150 milliseconds and the main flash for about 400 milliseconds. And when the shuttle pulses, it's only 80 milliseconds. So those numbers don't jibe. The shuttle should not be pulsing like that. And then I mentioned also that the faster object on the far right slows down a little bit in the left and right direction before it starts going up. And that doesn't work either. If an attitude adjuster rocket sends out an exhaust that pushes, it has to push all at once, and it can't slow down like this and go up like this. It's like driving a car in this direction and then turning right, and that's not the right way to move for something like that. This one, I'm not sure that I want to make a big issue of this. The exhaust plume would have to spread considerably to reach the main object. Well, it probably could do that, so we probably don't need to make a big issue of that. But these two are strong objections to almost to the level of a proof, but at this point we've got 5, and let's don't quibble about the number that we've got. So what does this all come down to? I've really tried to do a genuine, honest scientific inquiry into this. The reason I did it, of course, is because I didn't think the objects would end up being ice particles, and that implies that they are spacecraft, which would be a very important thing. But I tried to be fair in what I did, and I didn't push my conclusions, and at times it got to the point where I thought I would have to drop the whole thing because I got to points where I thought it was going to fall apart. Did not fall apart, and you've seen the analysis. There really is virtually nothing that supports the ice particle theory from the data that I have that are subjected to the analysis. And there are, on the other side of the coin, at least 5 proofs that the objects were not ice particles, therefore spacecraft. And they were either extraterrestrial or terrestrial, obviously. That's the dichotomy that we have. And if they were terrestrial, that implies a whole new level of technology that's levels and levels beyond anything that we have on this Earth. You saw some of those accelerations that we discussed, tremendous accelerations that would flatten any human pilot far beyond the capability of any craft that we have. So whether they're terrestrial or extraterrestrial, they're far beyond conventional programs. If they're terrestrial, that implies that we've been working on them for decades. Also implies that the Star Wars program is, I guess you might say, a sham, because we already have craft that are far beyond what we expected with Star Wars, and so that's been all kind of a waste of money. If they're extraterrestrial, it's really big news. We're being visited by other planets. It's also scary because those streaks that went through there, you can interpret those as well as I can. One possible explanation is that we were firing at them. That's a scary scenario. And so, once again, my analysis is a scientific one that at least satisfies me that those objects were not ice particles. And beyond that, we're all in the same boat together because we're speculating, and I have no evidence to prove what one was or the other, or whether one explanation works or the other, but it opens up the door, it opens up the can of worms to discussing some of these questions. And now, since we probably can see that these things were not ice particles but actually spacecraft, we can go one step farther and use the same type of analysis we did to calculate the velocities to calculate velocities at given distances and also accelerations at given distances. And I have done that, and I have a list of those here. And these are kind of mind-boggling to think about. We have, let's just start close to the shuttle. If it's about a mile away, that's getting pretty close to be shooting at something, I would think. But if it's about a mile away, we have an acceleration of about 10 Gs, and it gets up to 250 miles an hour. That's all right, and that's within normal capabilities, I guess. If it's as far away as 10 miles, it's accelerating at about 105 Gs, and it gets up to about 2,500 miles an hour in 1 second. To give you an idea of what 105 Gs would be like, if we assume that if you crash into a brick wall, if you assume the car will give about a little less than 3.5 feet, what that means is 100 Gs would be about like crashing into a solid brick wall at 100 miles an hour. The only problem is that would all happen in less than a 20th of a second. So 100 Gs for 1 second, or 1.7 seconds actually, but let's call it 1 second. 100 Gs for 1 second is like undergoing 20 100-mile-an-hour crashes into a brick wall, one right after the other. That's what 100 Gs is like. And we're just getting started here. If these objects are 100 miles away, it's 1,000 Gs, and 1,000, 10,000 Gs, and amazing velocities, up to the point where if it happens to be at the horizon, it's 18,000 Gs and gets up to about 430,000 miles an hour in 1 second. And anywhere up in this range is more Star Trek rather than Star Wars. So we're talking about some pretty tremendous accelerations and capabilities in spacecraft, given that they're as close as 10 miles or beyond from these things. I can't prove the distance, but 10 miles is fairly reasonable, I guess, and we're already far beyond what any human pilot could withstand, and we're starting to get into craft that are far beyond any capabilities that we have right now. So we've got something pretty incredible happening here. And one thing we have not mentioned in all this either, because I'm trying to explain this in terms of ice particles, is that we saw it in the video earlier when we looked at the tape. There are two streaks that go through there. Coincidentally, after the main particle accelerates away, there's a streak that came through there. What was that? And there's another streak that came over to the right where some of the other particles were when they accelerated too. And the fact that there were two flashes, a pre-flash and a flash, is somewhat of a coincidence with those two streaks. And so I'm not really saying what those have to be. I don't have any evidence that indicates what they are. But one interpretation certainly is that they were missiles of some kind being fired, and that's what some people have said.
Is that a possibility? For a missile to come through the atmosphere the way that that one occurred?
Yeah, that would work. Yeah, some people have suggested that's a laser. It couldn't have been a laser. Lasers go immediately from one point to the other, as far as we're concerned.
No,
the
this
speed
was
of light. It streaked through there. Yeah.
Would a rocket appear like that, though?
Well, it would have a contrail, I think. It could have a contrail.
So that's probably what's being seen, not the rocket itself.
Yeah,
but
that's right. Yeah.
If that's the case.
Sure, that's right. So there are interesting interpretations that you can have.
So there's no other possibility for that streak?
Well, I don't really want to say that.
What's NASA's position on that aspect of it?
The four scientists that looked at this film and said that the objects were ice particles did not comment on the streaks. And that's a strange omission in my opinion.
Yeah.
And at this point, we can all interpret what the thing might be. My point is that I set out to prove one way or the other whether these things were ice particles, and I'm pretty well convinced that they could not have been ice particles. That really just opens up a can of worms.
Where do you go with this now? I mean, you know, now that you've collected the data and you have it as something that you can present.
Well, I'm going to speak probably at some more of these triad conferences, but maybe with a larger circulation will come from the fact that this has been partially supported by the Funds for UFO Research. And so I will file a final report with them, and then they will circulate it too.
Let me ask you this. This always strikes me as odd, but I mean, NASA must know what this is. No? Yes? No? They must have some idea. I mean, they're the ones up there operating these shuttle missions.
I want to clarify, we are speculating, but within that framework, I'll speculate if you want. You'd think so, that they would know that something funny is going on. Unless, again, you can't think for people. I'm sure that some people would look at those and just say they must be ice particles.
Well, I want to look at, I mean, you must know something about the organization since you do contact with them, or you?
Yeah, in fact, I spent the summer of 1991 at Marshall Space Flight Center studying the surface of the sun, doing some of that work on supergranules. And the people that I met are just generally good scientists, very smart people, and they go home at night and watch television, whatever. And for the most part, just really are only casually interested in UFOs. The word UFO wasn't mentioned the whole summer when I was there.
Okay.
So I can easily see how people would just not even want to think that those might be UFOs, and they would look at it and say, well, ice particles is good enough for me.
Yeah.
And so,
So in a sense, even within NASA, the general attitudes transfer to the general public. Most people assume that NASA knows everything, you know.
Yeah, it's not like they're all out there hiding this from us. That's the farthest thing.
Mm-hmm.
They're just people like us, and they look at it and they probably wonder about it too.
Nose gear touchdown. 10. TLS go for main engine start.
Set T-minus 6, 5, 4. We have main engine start. 3, 2, 1. Booster ignition and liftoff of Columbia on a life sciences mission for Earth and space.
Houston's now controlling. 3 good engines at 100%. Altitude 115,000 feet, downrange distance 18 nautical miles. Altitude now 222,000 feet, downrange 48 nautical miles.